Welcome dear aspirants and enthusiasts. Thank you for revisiting our channel. Today we are going to discuss a problem from IIT JAM 2021. Okay, let us come to the problem. So this problem appeared in IIT JAM 2021. This problem is based on infinite square well potential. Here the particle has mass m and width of the square well is L. Here the wave function is a superposition of two eigenstates of Hamiltonian. Also note here that the coefficients of the wave functions are 1 by root 3 and root 2 over root 3, which suggests that the wave function is already normalized and we don't need to worry about the normalization constant as this wave function is already normalized. So based on these facts, we have to check the following answers, whether these facts are true or not. Delta p is square root 3 upon 2 h over L and expectation of p is 0, uncertainty in position is 0 and energy's expectation value is 3h square upon 8ml square. So we need to verify these facts and the informations are given as above. So how we will progress? While solving this problem, we will revisit some generalized relation and try to find the solution in details, and for that we will solve for the general scenario, as you can see that, and also we will calculate the expectation value of p square, x square and Hamiltonian, and obviously from that you can calculate the uncertainty or standard deviation. Okay. So this is the overview of the topics that we will try to touch while solving the problems. So we will try to encounter some old stuffs and some integrals, and then we will find the uncertainties for momentum, position and energy. And finally we will verify the facts that have been given. So if you have idea of dummy indices or you are a master of dummy indices, you can skip this slide easily. The timestamp has been given in the description box. Please check it out and you may skip this slide. So here we will study the effective way to multiply two summations. Suppose S is C1 psi 1 plus C2 psi 2 plus C3 psi 3 and so on, where psi's are basically arbitrary function. For our scenario this will be wave function. So make this summation pretty nice by rearranging in this way. So this can also be written as this, where instead of n we have used m. So as you can observe, this index n can also be written as m, as they are just to signify the range of the sum and has no other importance till now, so we can call them dummy indices. We will further call this summation of arbitrary functions with proper coefficient as wave function and will treat it as psi of x. Okay, coming to the next part. We wish to calculate the product of two sums. So if we wish to do so, we can write it as p equals to s dot s, and explicitly we can break it out. So in left hand side the sum is written explicitly, and in right hand side we have written it in implicitly or in shorthand notation. So calculate the left hand side and you can calculate this easily, and you will find this term c1 square psi 1 square plus c2 square psi 2 square plus c1 c2 psi 1 psi 2. So this cross term will appear, c1 c2 c2 c1. Okay, so this term will appear here. So that will not be obvious on right hand side if you don't use two other indices for doing the product. Okay, original problem. While calculating the measurable quantity, one can proceed as follows. If O is an observable or operator, we can calculate its value or its expectation value as this way: psi star O psi dx, integration over 0 to L. So this can further be further broken out into two parts. Okay. So this psi or psi star has been written explicitly, and if we proceed further, we can put this cn cm out of the integration and we will find that this will give us a term summation of Cn star Cm, and other term will be the integration of Cn star psi m. So this integration, this is basically your integration on the basis eigenstates, not on the given original wave function. So that will be very helpful while calculating the expectation value of any observable with arbitrary state. This formula enables us to calculate the expectation value of any observable for any arbitrary state in terms of basis eigenstates. Now let us calculate the expectation value of the momentum operator. This can be defined as follows. We can further break it down in terms of basis eigenstates. Okay, so this looks like now that. Now put the functional structure of the momentum operator. So this will be h cross over I ddx. Now further put the explicit structure of the basis eigenfunctions, and this will be like that. So the basis eigenfunctions will be sinusoidal, and we put different indices here m and n to generalize the expression. Okay. So when we calculate further, you can see that in summation, not only Cn and Cm will be there, but also a factor of m will be there, which will come from the derivative term. Okay, so remember this fact. This will be crucial for calculation. So this expectation value of momentum can be written as this. So you can easily guess the result. Yes, it will be 0. As you can see that the integral give you the real eigenvalue, and the coefficients are also real in the problem. But being a Hermitian operator, momentum operator should possess a real eigenvalue. But in the expression you can see there is a I. So the result should be 0. Okay, but however we will go through the calculation, and we will show how this 0 can be achieved. Okay, so remember this extra m factor, that will be very much crucial. So let us now break this summation. So you will have two terms, one with n equals to 1 and m equals to 2, and another will be n equals to 2 and m equals to 1. And the first term, in first term you will get a extra 2 factor due to that m Cn star Cm factor. Okay, so this 2 factor will come when m will be 2. Okay, so you may be thinking that why we have not taken 1 1 or 2 2 term in this, because the associated integral will vanish. Trust me for now, and I will show you how this 1 1 or 2 2 term will vanish. I will show it very soon. Trust me now. Okay, further when you calculate these terms, you will get these terms like 4L by 3 pi, 8L by 3 pi. I will show this calculation also, but for being now, trust on me. So whole calculation give you a result 0. So expectation value of momentum operator is 0. What does that mean? That means the average value of the momentum in a particle in a box is 0. But remember, the energy is not 0, although the expectation value of the momentum operator is 0. That here we have the product term which contains sine and cosine both, and we have chosen when this two indices m and n, they are not same, we will pick the integral, and when they are same, we have neglected the terms. Why we have neglected them? I will come to this. Okay, so I have calculated here 4 integrals. Firstly, this one sine and cosine with different indices. Then I will calculate sine and cosine with same indices. Further, I will calculate 2 sine terms with same indices, and finally I will calculate 2 sine terms with different indices. Okay, so as I had promised, I will show you how to calculate these integrals, but I guess all you know this integration much better, so I will just show you the results along with the steps without explaining it in much more details. Okay, so you can pause the video and check the integrals. So first integral was trivial. You can do the pretty trigonometry and you will finally land to this formula. And in our case we have chosen m and n different. So when m is 1 and n is 2, when n is 1 and m is 2, what will be the result? You can check it easily. So further steps are like that. So you can check this. Okay, let us now calculate the expectation value of the square of the momentum operator. This can be broken as follows. Now put the explicit form of the p square operator. So when you put this, you will finally land to this form, and when you take the derivative twice, you will get a term which contains m square. So this is crucial for our calculation, this m square term. And also you can see that we have the integral where we get two sign terms where n and m are in general different, but they can be same. So in our previous calculation in integral slide, you can check that if n and m are same, they will yield a value of L, whereas if n and m are different, they will yield a value of 0. That means you can get the expression of p square as this. The integral will give you L delta Mn. So this delta function, this Kronecker delta Mn, this will kill one of the summation. So when you kill one of the summations, you will get this term, and this Cm coefficient are given in your problem. Just put it and you will get easily this term, and this will give you 3 pi square h cut square over L square. Put the value of h cut, which is h over 2 pi, and you will land with 3h by 4 L square. So now it is very easy to calculate the standard deviation of the momentum, which will be uncertainty for it, and it will be simply square root of 3h over twice L, as expectation of momentum is 0. Okay, let us now calculate the expectation value for the Hamiltonian. So this can be calculated in usual way where you have to do the derivatives and all these stuffs, but this will be identical to the calculation of the p square. So I am not going to that way or that path, rather I will choose this thing. So the expectation of the Hamiltonian will be expectation of p square upon twice m plus expectation of potential, but within the box the potential is 0. So expectation of Hamiltonian will be 1 upon twice m expectation of p square. And in previous slide we have calculated the expectation of p square. So this will finally give 3h upon 8m L square. So this will be the expectation value of the Hamiltonian or expectation value of the energy. We have solved up to now. You are able to answer the MSQ problem. But let me show you the expectation value of position and its expectation value of the position square. So expressions have been given here. So I will not do the whole calculation here, but I can give you the results. So the results will be like that. So you can check that expectation value of position will be around 0.138 of L, and expectation value of x square will be around 0.33 of L square. So obviously the uncertainty in position will not be 0, remember it. So let us come to the problem. So as we have calculated till now, the first option, that is expectation of momentum, will be 0. So this one is correct, this fact is obviously correct. We have calculated the uncertainty in momentum, and that was simply square root 3 by 2 h over L. So this fact is also true. Expectation of energy was 3h square upon 8 m L square. So this fact is also true.